Alright, so before we dive down into division algorithm, let's take a quick look on what we are trying to do. So we look at this digital perspective of binary division. Let's say we pick up the same example as in the first slide we have shown, and but let's fix that. Okay, my number of bit is 8-bit. Okay, so with the 8-bit example, my dividend is 00110101 and my divisor is 00000111, and we store this 8-bit dividend and divisor into a 16-bit storage, which we call register, right? So 16-bit storage or register, we stored them, and we stored them, the dividend goes into the lower half of one of the register, we call it a remainder register, and divisor goes into the upper half of another 16-bit register, we call it a divisor register. The remainder register is populated with a dividend at the lower byte side, and divisor is loaded on the higher byte side of a divisor register. Both are 16-bit for a 8-bit division process. And a quotient, which has a left shift capability, is 8-bit register. We initialize with all 0. So we start with the quotient value as all 0. Now what we do in the iteration 1, here is this in the slide, in this demonstration, we are showing that this is iteration 1, and we first do a subtraction of divisor value from the remainder value, all 16-bit. So of course what happens, right, in the very first step, it's always this, your subtraction result is going to be the negative one. And by the way, we are assuming we are representing these values in 8-bit 2's complement format. So we got a negative remainder, and then what we do is, if it is a negative remainder, left shift quotient by 1 and insert a 0 at the LSB of the quotient register. So left shift quotient by 1, whole bit pattern shifted towards the left, and we insert a 0 in the LSB position. That's basically, in a logical operation sense, it's a left shift 1 or with a 0. Then next step is important. In the same iteration, you roll back the remainder. So if my remainder as a after subtraction, that remainder is now containing a negative, we roll back by addition. Okay, and then we right shift the divisor by 1 bit, and that brings to us next iteration, or iteration 2. In the iteration 2, we follow the same process. We subtract divisor register from the remainder register, and check the sign of the remainder value. It's of course negative, so we quotient register, we left shift by 1 bit, insert a 0, and roll back the remainder and right shift the divisor. So probably you now notice that we are bringing the divisor bit pattern gradually under the dividend bit pattern, as if we are trying to find out some bit pattern of the dividend which become more than the divisor bit pattern, right? We are kind of shifting the divisor, making really under the scope of the dividend bit pattern, and trying to find out digitally that at some point of time my divisor register will contain less value than the remainder register contain. So till now it's not that point. We subtract, we see that's a negative, we insert a 0, roll back the value, right shift divisor. Subtract, still it is, will give a negative remainder, we insert a 0, roll back, right shift the divisor. This one also, now till now remainder is as of higher value than, remainder has lower value than of the divisor register. We do the subtraction and look at the remainder negative. We left shift quotient by 1, insert a 0, roll back the remainder register, divisor, right shift by 1 bit. At this point, it's still divisor has a higher value than remainder. That means with subtraction we'll get a negative value. Then we left shift quotient by 1, insert a 0, roll back the remainder, and divisor right shift to 1. Now this position, if you look at this bit pattern, this is same as the very first step we did for the paper pencil method, right? We placed 111 under 1101, right, and then did the subtraction. So at this point, what will happen? After subtraction, your remainder is a positive value. With that, what we do, we left shift positive remainder, we left shift the quotient but insert a 1. Okay, so it is quotient left shift by 1 bit or with a 1. And then right shift the divisor. There is no rollback because if it is a positive remainder, there is no rollback. Now iteration 8, we subtract, that's still a positive, so we insert a 1 into the quotient, right shift the divisor, subtract, a remainder is positive, we insert 1, and that's end of our process. Now, so quotient become 0 0 0 0 0 1 1 1, where remainder becomes 0 0 0 0 0 1 0 0. Now you need to note the iteration number. See, we started with the 8 bit, but till we are at the beginning of the iteration 9, not the end of the iteration 9, we are not done. So for 8 bit, we need to do 9 iteration with this algorithm. For 32 bits, you need to do 33 iteration. Okay, please note that while we are studying this in our algorithm for binary division.